Voltage stability is one of the most critical aspects of modern power system operation. While the public usually focuses on active power, MW, the reliable operation of an electrical grid depends equally on reactive power, VARs. Active power performs useful work such as driving motors, producing heat, and powering electrical equipment, whereas reactive power maintains the electric and magnetic fields required for transformers, transmission lines, and rotating machines. Without sufficient reactive power, acceptable voltage levels cannot be maintained, leading to voltage instability and potentially widespread blackouts. Experience from major power system disturbances has shown that voltage-related problems are among the leading causes of large-scale outages. Events such as the Iberian Peninsula blackout demonstrated that inadequate reactive power support can rapidly evolve into cascading failures affecting an entire interconnected grid. Consequently, voltage stability is no longer viewed as a secondary operational issue but as a fundamental requirement for maintaining system security. Reactive power differs fundamentally from real power. Real power represents energy transferred from generators to consumers and converted into useful work. Reactive power, on the other hand, oscillates between the source and the load, supporting the electromagnetic fields required for AC system operation without performing useful work directly. Together they form the apparent power of the system, while the ratio of real power to apparent power defines the power factor. Maintaining a good power factor improves transmission efficiency, reduces losses, and preserves system capacity. Maintaining voltage requires a continuous balance between reactive power production and reactive power consumption. This balance can be visualized using the concept of a reactive power tank. Reactive power sources include synchronous generators operating with appropriate excitation, lightly loaded transmission lines, underground cables, capacitor banks, static VR compensators, SVCs, STATCOMs, and imported reactive power from neighboring systems. Reactive power sinks include heavily loaded transmission lines, transformers, induction motors, underexcited generators, and exported power flows. If reactive power generation exceeds demand, system voltages increase. When demand exceeds supply, voltages decrease. Therefore, transmission system operators continuously regulate reactive power using automatic voltage regulators, transformer tap changers, capacitor switching, reactor switching, and generator dispatch. An important characteristic of voltage control is that it is highly localized. Unlike system frequency, which remains nearly uniform throughout an interconnected network, voltage varies from bus to bus depending on local generation, load, network impedance, and reactive resources. Reactive power cannot be efficiently transported over long transmission distances because of significant losses and voltage drops. Consequently, voltage problems must be solved close to where they occur. This principle has become increasingly important as traditional synchronous generators are replaced by inverter-based resources such as wind farms, solar photovoltaic plants, and battery energy storage systems. Modern inverter-based resources can provide reactive power support even when producing little or no active power, but achieving this capability requires advanced control strategies, suitable grid codes, and coordinated system operation. The theoretical basis of voltage stability is illustrated by the relationship between transmitted power and receiving end voltage. As active power transfer increases across a transmission corridor, transmission current also increases, producing larger voltage drops due to line impedance. Initially, voltage decreases gradually, but eventually a maximum power transfer limit is reached. Beyond this point, no stable operating solution exists, resulting in voltage collapse. This relationship is represented by the well-known power voltage, PV, curve, commonly referred to as the nose curve. The upper section of the PV curve represents stable operating conditions where the system naturally returns to equilibrium following small disturbances. The lower section represents unstable operating conditions where any disturbance causes further voltage decline. The distance between the current operating point and the nose point defines the voltage stability margin. Two important security indicators are the voltage margin, which measures the remaining voltage reserve before collapse, and the power margin, which measures how much additional power can be transferred before reaching the maximum transfer capability. System operators strive to maintain adequate margins under both normal operating conditions and contingency scenarios because operating too close to the nose point significantly increases the risk of voltage collapse following equipment failures or sudden load changes. Reactive compensation devices such as capacitor banks, SVCs, StatComs, and synchronous condensers improve voltage stability by shifting the PV curve toward higher transfer capability, allowing greater power transmission. However, reactive compensation must be carefully planned because excessive dependence on capacitive support may create new operational challenges, particularly during dynamic disturbances where switching delays or equipment limitations reduce effectiveness. Furthermore, the location of reactive compensation is often more important than its total size, emphasizing again that voltage support is fundamentally a local phenomenon. Real power systems are considerably more complex than the simple PV curve suggests. Voltage stability depends simultaneously on loading conditions, generator dispatch, network topology, reactive power availability, equipment status, contingency conditions, and dynamic control system responses. Load behavior, transformer tap changers, automatic voltage regulators, protection systems, and generator excitation systems all influence system stability. Therefore, utilities complement static PV curve analysis with continuation power flow methods, small signal stability studies, and time domain dynamic simulations to obtain a comprehensive assessment of voltage security. Voltage instability occurs over different timescales. Slow voltage collapse develops over several minutes and is typically caused by gradually increasing reactive power demand. Transformer load tap changers attempt to restore customer voltage by increasing reactive power consumption, while generators eventually reach their overexcitation limits and lose the ability to supply additional reactive power. These mechanisms reinforce one another, creating a progressive voltage decline that may ultimately lead to collapse if corrective actions are not taken. Fast voltage collapse develops within seconds or even cycles after a major disturbance. A common mechanism involves induction motors. During severe voltage depressions caused by faults, motors slow down or stall. When the fault is cleared, stalled motors require very large reactive currents to accelerate again. If sufficient dynamic reactive support is unavailable, voltages continue falling and recovery becomes impossible. Modern inverter-based resources also influence fast voltage dynamics because inadequate fault write-through capability may cause renewable generators to disconnect during voltage dips, removing valuable reactive power support precisely when it is needed most. Historical case studies clearly illustrate these principles. Studies of voltage collapse in the Pacific Northwest demonstrated that insufficient reactive reserves caused transmission voltages to decline continuously over approximately 25 minutes following an initiating disturbance. Additional reactive support through synchronous condensers, StatComs, capacitor switching, or coordinated generator redispatch successfully prevented collapse and restored acceptable voltage levels. These studies emphasize that early operator intervention is significantly more effective than delayed corrective actions after voltage deterioration accelerates. Synchronous generators remain among the most valuable voltage control devices because they independently control both active and reactive power. Mechanical input determines active power production, while excitation current controls reactive power output. Increasing excitation enables generators to supply reactive power and raise system voltage, whereas reducing excitation causes generators to absorb reactive power and reduce overvoltage conditions. However, synchronous generators operate within well-defined capability limits represented by the generator capability curve. Rotor thermal limits restrict maximum reactive power production, while underexcitation limits are imposed by stability considerations to prevent loss of synchronism. During heavily stressed operating conditions, these physical limits may prevent generators from supplying additional reactive power even when system voltage continues declining. The increasing penetration of large data centers introduces new voltage stability challenges. Multi-gigawatt data center clusters substantially increase local reactive power demand and may move system operating points closer to voltage collapse limits. At the same time, many modern data centers incorporate advanced power electronics capable of providing voltage regulation, reactive power support, and other ancillary services. Proper coordination between transmission operators and large industrial customers therefore represents both a challenge and an opportunity for future grid operation. Several fundamental principles emerge from modern voltage stability analysis. Voltage problems are local and require local solutions. Maintaining sufficient voltage and power margins is essential for secure operation. Slow and fast voltage stability mechanisms interact and must both be considered during planning and real-time operation. Voltage stability depends on both generation-side and load-side behavior, particularly as inverter-based resources and electronically controlled loads become increasingly common. Historical blackout events continue to provide valuable lessons for improving operational practices, planning methodologies, and protection strategies. As electric power systems continue evolving toward higher renewable energy penetration, distributed generation, battery energy storage, and electrified loads, the underlying physics governing voltage stability remain unchanged. Reliable operation will continue to depend on maintaining an appropriate balance of reactive power, respecting equipment capability limits, preserving adequate voltage stability margins, and coordinating planning, operational control, and market mechanisms to ensure secure and resilient power system performance. Voltage stability remains and will likely remain a central concern for power system reliability as grids evolve to accommodate changing resource mixes and demand patterns. Several overarching principles emerge from the foregoing discussion. Location dictates solutions. Voltage problems are inherently local. Effective remedies must be deployed proximate to problem locations. One-size-fits-all approaches rarely succeed across diverse network topologies. Margins matter, both voltage margins, distance to V critical, and power margins, distance to Pmax, provide essential security indicators. Adequate margins under credible contingencies form the bedrock of reliable operation. Timescales interact. Slow and fast voltage dynamics are not wholly separable. Slow mechanisms set the stage upon which fast dynamics play out. Comprehensive assessment must address both regimes. Generation and load are both critical. Traditional focus on generation-side capabilities must expand to encompass load-side characteristics, particularly as large controllable loads gain prominence. Historical lessons inform future preparedness. Events like the Iberian blackout and U.S. Northwest collapse studies offer invaluable empirical grounding for theoretical understanding. Studying past failures helps prevent future recurrences. Coordination is essential. Achieving robust voltage stability requires coordinated action across planning horizons, long-term infrastructure investment, operational timeframes, real-time dispatch and control, and market mechanisms, properly valuing reactive services. Siloed approaches leave gaps that disturbances can exploit. As power systems continue transitioning toward higher penetrations of inverter-based resources, electrified end uses, and distributed generation, the fundamental physics underlying voltage stability remains unchanged even as the specific manifestations and optimal management strategies evolve. Maintaining vigilance regarding reactive power balance, respecting equipment capability limits, and preserving adequate stability margins across all operating conditions will remain enduring imperatives for reliable power delivery.